Good morning or good afternoon. My name is Atar Azizin Amini, Director of the IBT/ABCUTC at Florida International University. Very warm welcome to more than almost 1,200 sites that have registered to listen to us live for our July 2026 monthly webinar. We are happy to bring to you a webinar entitled Structural Design with Ultra High Performance Concrete. We are glad to have with us Dr. David Garber, who is with the Federal Highway Administration, and Dr. Rafiq Hilu, also with the Federal Highway Administration, as a speaker for our monthly webinar. Just a couple of updates on our upcoming conference, 2026 World Bridge Engineering Conference. The conference is sponsored by 33 co-sponsoring DOT. We thank you, every single one of them. 140 technical presentation is going to be presented. We have keynote talks. More than 40 exhibitors have reserved their booths. There will be receptions, and also there will be award program. Also, in addition, we are going to have 3 workshops on half a day on the what bridge engineers should know about the AI, a workshop all day long on non-destructive testing, and then also on sprayable UHPC. Please note the date. That is December 4, 2026. More importantly, there is also a call for awards. Deadline, the award is still is open until the end of the September. You can submit your nomination. There are several different categories. Registration is open. December is a very busy time, as you might guess, in Miami, Florida. So we have a block of room at a special conference rate, but those are going really fast. So please reserve your hotel room if you like to at a special rate as soon as possible. By the way, we are going to put the PDF copy of all these slides on our website. So all these references that you see, you can access to them after the webinar, about a week after the webinar. As I mentioned, more than 40 exhibitors have reserved their booths, but there are few additional booths that are still available. If you are interested, please go ahead and look at our website. There's a procedure to reserve your booths. There is one of the workshop, which is December 4th, in conjunction with the World Bridge Engineering Conference. We are also working with the Georgia DOT in 2027 to have another workshop in Atlanta. So more information will be coming next. But the first one is going to be December 4 in conjunction with the World Bridge Engineering Conference. And in order to attend the workshops, you have to be attending the conference. So it's only for the conference attendees. Also, the first US DOT Annual Transportation Infrastructure Summit will be held. This is a separate event, but in conjunction with our 2026 World Bridge Engineering Conference. I just put this slide. There is a special issue of the MDPI dedicated to UHPC. I just put these slides. We are going to be sharing more information during our next monthly webinar. So at this point, I'm going to turn it to Kathy Kroll, who is going to share with you some additional information related to bridge engineering. Kathy, it's all yours.
Thank you, Atorad. I'm Kathy Kroll. I'm a co-director of technology transfer for the IBT ABC UTC at Florida International University. I'd like to thank you, and as Atorad mentioned, roughly 1,200 other registered sites who are joining us for today's 184th webinar in our monthly webinar series. Before we get started with the presentation, I'd like to share some upcoming industry events. First, on September 8th, we'll be presenting our annual in-depth web training. The in-depth web training from the IBT ABC UTC is similar to this webinar series, but it goes from 11 a.m. to 3:15 p.m. Eastern, which gives us additional time to delve deeper into a particular topic. This year's topic will be accelerated and innovative bridge deck repair. Our speakers include Graham Bettis, former Texas DOT bridge engineer, talking about making the decisions to repair versus replace. David Whitmore with Vector Corrosion will be talking about the corrosion management topics. Charlie Young with BDI will be talking about non-destructive testing methods to help with making decisions and scope definition. And Tristan Sigel with Colorado DOT will be presenting case studies with focus on installation methods. Please mark your calendar for this event. Registration is open on the IBT ABC UTC website. Next is the Precast Prestressed Concrete Institute's Committee Days Conference, to be held September 9th through the 12th in San Antonio, Texas. ASBE, the American Segmental Bridge Institute, will be holding their 38th annual convention in San Antonio, Texas, November 9th through the 11th. Continuing to our own events, our next research seminar will be held July 31st, which is next Friday. The topic is using dogs and magnetic field to accurately detect corrosion in steel strands embedded in concrete. Our own Dr. Aziz Namini will be presenting, along with Dr. Furton and Carlos Concha Avila from Florida International University. Our next monthly webinar will be on Thursday, August 27th from 1 to 2:15 Eastern. Note this is later in the month than our typical webinar. Caltrans will be presenting on their BIM for Infrastructure program. I'm really excited about this particular webinar. It has a lot of really interesting topics that are really relevant to bridge engineers right now, related to the building information modeling and digital delivery. That's all for our announcements. So on to our standard housekeeping items. As many of you know, these webinars are recorded and posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation is provided to the archives. Lastly, this presentation will be followed by a question and answer session. We have a number of questions that were submitted with registration. So on to our presentation. When we talk about UHPC, Dr. Benjamin Graybill with the U.S. Federal Highway Administration is always involved, as he's been a leading proponent of research and implementation efforts for the material. Ben was not able to join us today, but he sent his regards and provided a short introduction that I will now share. So this is Ben's words. A big thank you to the IBT ABC UTC for giving us the chance to enable innovation through this month's webinar. As I'm sure most people know, UHPC is an advanced type of fiber reinforced concrete with high strength and very good durability. But at the end of the day, we're less concerned with the material properties and more interested in its ability to address your needs. My colleagues and I developed with this deployable, innovative solutions, and UHPC has enabled quite a few of them. 15 years ago, UHPC caught the attention of bridge engineers when it began to be used to enable accelerated construction by simplifying connection details. 10 years ago, UHPC-based preservation activities like bridge deck overlays and steel beam end repairs started changing how bridge maintenance is done. And in recent years, the focus has expanded even more, looking towards primary bridge components like pre-tensioned girders that can span longer distances, reduce dead load, and achieve shallower depths. The interest in primary components drove the need for former structural design guidance, which ASHTO published in 2024, and which in 2027 will be expanded to include material qualifications and quality control processes. My colleagues and I have been heavily involved with all of these efforts, and we're excited to continue to collaborate with the community to build better bridges. With that, we'll start our featured presentation. We're happy to welcome Dr. David Garber, Senior Bridge Engineer with the Office of Bridges and Structures with FHWA, and Dr. Rafiq Helou, Research Structural Engineer with the Office of Infrastructure, Research and Development, also with FHWA.
Thank you for the introduction. So today we're going to talk to you about the structural design with ultra-high performance concrete. Before we start, I'm just going to go through quickly a few disclaimers. So the US government does not endorse products or manufacturers. So if you see those in this presentation, they're only here because they're considered essential to the objective of the presentation. They are included for informational purposes only and not intended to reflect the preference, approval, or endorsement of any one product or entity. Except for the statutes and regulations cited, the content of this presentation does not have the force or effect of the law. It is intended only to provide information and are not meant to bind the state or the public in any way. The approaches or methods discussed in this presentation are not federal requirement unless otherwise noted. And unless otherwise noted, Federal Highway is the source of all images in the presentation. So with that quick outline, so throughout this presentation, we're going to start by talking about what is UHPC and where is it currently used. Then we're going to go over the basic design steps that an engineer would follow to design a UHPC bridge before we conclude and answer any questions you might have. So what is UHPC? UHPC is still concrete. It is made of similar ingredients that you'll see in conventional concrete, but the proportions and the gradations are different. So the image you see here represents the composition of conventional concrete and UHPC based on mass percentages. As you see, UHPC has a higher percentage of cementitious materials. It does not contain coarse aggregates, so you'll see only very fine aggregate or fillers in UHPC. It has a very low water to cement ratio, about 0.2 typically, and it contains short steel fibers. The image on the right-hand side, it shows a microstructure view of conventional concrete compared to UHPC. So you can see here the coarse aggregate, they're typically about 1/4 inch to 3/4 inch in size. You won't see that in UHPC given that it does not have any coarse aggregates. What you'll see are those shiny dots that you see on the UHPC picture. Those are the steel fibers in the matrix. Typically, steel fibers are included at 2% by volume. In terms of mechanical property, UHPC, again, it's still concrete, but it has a very, very high compressive strength. The picture on the left-hand side shows a comparison between the compressive stress strain curve of conventional concrete in dark gray compared to UHPC in red. As you can see, UHPC is about twice as stiff as conventional concrete, 2 to 6 times stronger in compression, with the compressive strength ranging with a minimum of 17.5 and can go up to 24 KSI with ambient cure. You can go more with different curing treatments. More importantly, though, and where UHPC stands in the realm of conventional concretes is its ability to carry tension. And only it can carry a high tensile strength, but also it can sustain that after cracking. What I mean, if we take a stick of conventional concrete and you apply tension on it, you will see that it will carry some tension. I have either stress maybe around 0.4 to 0.6 KSI, that's typically. However, and then it cracks, and once it cracks, it splits into pieces. And then the load directly drops down to 0. However, take a stick of UHPC and you start pulling on it, you'll get the stress strain curve I'm showing here on the screen. UHPC has fibers in it, and those fibers bridge that first crack. So it stops that crack from growing, reinforces it at that location, and then another crack will form. The fibers over there also reinforce that crack, stops it from growing, then another will form. And then you enter what we call a multiple cracking phase, where multiple cracks are forming and being bridged. And those cracks are very, very small. You can't really see them with the naked eye. So multiple cracks are forming, they're being bridged by those fibers, but the cracking stress within that multiple cracking region is maintained with increasing strain or even exceeded. And that behavior continues until the fiber bridging capacity is exhausted and the fibers can no longer hold these tight cracks together, that one of these cracks starts to open up and the fibers, what we call the localized crack, and the fibers in that starts to pull out. That phenomenon we call the crack localization. And this crack localization point is very important property in UHPC because after that, the tensile capacity starts, this is the crack localization point, tensile capacity starts to drop with increasing deformation, and the deformation starts to localize all into that one crack that continues to open up. The tensile stress, the effective cracking stress or the first cracking stress of UHPC ranges between 0.75 KSI all the way up to 1.8. Crack localization starts minimum equal to the effective cracking strength, so about 0.75. It can go up to 2 KSI. And the crack localization strain, that point at which beyond that you'll start losing tensile capacity. That strain is about 0.025 and can go up to 0.006. But that's not all. Another very important property for UHPC is its high durability. UHPC has a very dense matrix that has a discontinuous pore network. What that means is that it results in nearly impermeable, and that prevents water ingress, which protects the integrity of the UHPC itself, but also protects the reinforcement from corrosion that's inside. So to demonstrate this, what I'm showing here is a U.S. Army Corps of Engineers durability testing facility on Treat Island in Maine Bay of Fundy. This island is known to have some of the world's largest tides and harshest environment for concrete, with 2 cycles of low and high tide per day, and with potential freezing and unfreezing in cold temperatures. After 11 years where UHPC samples were put there, after 11 years of exposure, the UHPC samples had minimum deterioration. You'll see those brown spots there. Those are local corrosion of fibers that went away, but it's cosmetic. Nothing goes into the section itself. I don't have a picture for similar conventional concrete samples because typically they would completely disintegrate within this time frame at that facility. There are many different applications that take advantage of these enhanced properties of UHPC. It's good bonds well with conventional concrete. It has very good durability, nearly impermeable, high compressive strength, sustained post-cracking tensile capacity. So a lot of applications take advantage early on, started to take advantage of those. I'm showing some of these applications on the screen here. Of note are the UHPC connections between prefabricated elements. Those could be new construction or repair of existing connections, repair of deteriorated ends of steel girders, UHPC overlays, and link slabs. There have been also several full-scale bridge component applications. The applications were targeted early on. They were targeted on, one, testing how this technology performs in real life on a bridge under traffic, and also served as a proof of concept that we can make, design, and build bridges made fully of UHPC. Many of those applications were in Iowa, and one more recently was built in Michigan. The first deployment was in 2005, so about 21 years ago, with no sign of deterioration or damage so far. The map you see here on the screen has many dots, hundreds and hundreds of these dots. Each dot represents the location of a bridge that has utilized UHPC and that's still open into traffic today. We filtered those dots based on the application. So what you're seeing here on this is an evolution, also the total number of UHPC applications and bridges with respect to the years, so throughout the years. As you see, many of these applications use UHPC in connections. The second most used application was preservation and repair and bridge overlays. While there are some structural applications of UHPC, the majority, as we said, is not, primarily because there was no structural design guide that allows engineers to utilize the enhanced properties in structural design and build those new components efficiently. But that has changed today, and we can make structures with UHPC. It is now a possibility, and that changed with the publication of the AASHTO Guide Specification for Structural Design in 2004. The guide, it parallels Section 5 of the AASHTO LRFD Bridge Design Specification and only contains guidance that is different for UHPC than conventional concrete. If it's designed the same way, if there is no change, the guide refers you back to the relevant section in the LRFD. In general, what you'll see in this presentation and in the guide, that the design process for UHPC follows the same basic engineering mechanics and mechanics of material concepts that you are familiar with and that you use in conventional concrete design. However, it does incorporate the behavior of UHPC into the design process. So the changes come from that. Throughout this talk, you will see, so how do you design UHPC structural elements? You design it just like concrete, but now you can utilize the tensile capacity in design. That's for the first time. That's because of the sustained post-cracking tensile capacity. The way we do that is by utilize a new mechanical model in tension that describes the behavior of the UHPC in tension. Generally, that model mimics the stress strain response that you obtain from a direct tension test. So it is a elastic plastic model, and what I want to point out that it does stop right at the point of crack localization. So that is the point where beyond that you will start seeing a drop in tensile stress. So you start to lose that bridging capacity of the UHPC and the load starts to drop in tension. So that is the point where the model would stop the behavior. You design UHPC just like concrete, but now with the introduction of the tensile capacity in the design, a new failure mode will need to be checked, and that's related to the loss of the tensile capacity. So That failure mode will be checked and designed for typically, and that is covered in the guide. The picture here on the screen that shows a flexure, a UHPC girder tested near Turner Fairbank in flexure, and this one is in shear. As you can see, that is the crack that you'll see around the point of failure, which corresponds to the crack localization of the material at the point at which you start to lose that tensile bridging capacity. New designs are possible with UHPC. Again, thanks to the tensile capacity given by the fibers. The UHPC gives you a less or reduction. It allows you to reduce the need for auxiliary reinforcement, such as those used for temperature and shrinkage. Also reduce congestion of reinforcement when the reinforcement is needed. UHPC can carry a lot of shear force, so there is no need to add sometimes transverse shear reinforcement unless they're structurally required, of course. To give you an example, the section you see here on the screen, on that side, all of them, these are modified precast concrete for economical fabrication, or PCEF section. The picture on the left shows the fabrication of a UHPC girders that was tested at Federal Highway. What you see here is all the reinforcement in the girder. So no auxiliary steel reinforcement, no transverse steel reinforcement in that specific girder. The pictures on the left are 3 girders, 35-inch deep, 43-inch deep for that middle one, and that one is 73-inch deep. They all have 3-inch web with no shear reinforcement. Here are a number of specifications and references that we'll use in this presentation. So the first one, like I said, is a reference to the ASH to LRFD bridge design specification. That's for conventional concrete. The ASH to guide that that's specifically for the design of UHPC. And we're also presenting 4 other references that could help you. That's published by Federal Highway, and those contain design example that can help you get started with the design of UHPC structural component. Okay, so let's switch gears now to talk about the design process. So let's remember the design steps you follow for conventional concrete when designing a bridge. So first, you'll determine the initial bridge layout, the girder sections, size, shape. You calculate moment and shear diagrams, steel reinforcement, whether you decide whether pre-stress, non-pre-stress, then you calculate service fatigue limit state, the strength limit state, and then you check deflections. The process to design UHPC structural element is the same, with 2 main differences that I'm highlighting here, and then we will kind of go into more in detail with them later on with David. So these are a strain check added for non-pre-stressed components at the service level, the service limit state, and also in the service limit state, there is another check, which is the principal tension stress check in the webs of girders in both pre-stressed and non-pre-stressed girders. So the first general step in the design is to determine the initial bridge layout, right? So like I said, the same basic principles, no change in here. So you still need a minimum of 4 beams or 4 girder lines or webs per span for redundancy. However, if you were to design the same bridge and you're trying to compare, what would that bridge look like if it was made of UHPC? Well, UHPC girders are stronger. So maybe what you can do is you can reduce a few girder lines. So if you're, for example, doing a 5-lane, 5 lines of girders, what a UHPC bridge might look like, you just need 4, so you eliminate 1 in that example. The higher strength of UHPC members also allows it to span longer. So for the same depth, you can extend the span. What that means is that if you can move that from a 3-span bridge to a 2-span bridge, which allow you for example, in that case, it will allow you more lanes of traffic underneath the bridge and also decrease the substructure cost because you're building one less pier. You may also want to eliminate a support in water. So in this case, you're eliminating, not only you're reducing the cost of building a pier in water, but also you're avoiding all the problems that come with that in terms of durability or scour concerns. The higher strengths of UHPC members also allow for shallower members. So they're lighter, they're more optimized, and that leads to lighter superstructures and reduce the demand on the substructure. Also, by being shallower, you can allow for a lower profile. Sometimes you have reduction in cost because you allow you to lower the profile and decrease the cost for the built-up of approaches going to the bridge. And with that, I'm going to turn it over to David to continue with the design process.
All right. Thank you, Rafiq. So I'll continue talking about or walking us through some of these design steps. So the next step in the general design process is to select your girder shape. And with UHPC, we can't just use the typical shapes that we have for conventional concrete directly. We need to modify them or optimize them some, because UHPC allows us to have thinner webs, narrower top and bottom flanges, and shallower section depths overall. With UHPC, we can also use larger diameter strands or higher strength strands, all on that same 2-inch by 2-inch grid that we use for conventional concrete. As I said, there aren't any current standard UHPC beam sections. So as states and owners are looking for early deployment of UHPC sections, we need to have some kind of strategy for these pilot projects or small deployments. And a good starting point is to start from our conventional concrete design standards. So what we can do is we can take what precasters have in their yards, we can modify them to take advantage of UHPC. FDOT has done this already with their H piles. So in early efforts, they've taken their square pile sections, added some blockouts, and cast some early UHPC beam sections to be able to research. And they're using that as kind of a starting point for their UHPC H-pile standard. Another example would be using bald T forms that a precaster already has, looking to see if we can slide those forms in to decrease that web width. We can add some blockouts in the top to further decrease the weight of the section, taking advantage of the higher compressive strength of UHPC. Maybe modify the bottom soffit if we need to, and then cast the UHPC in that modified form. So again, you could use any formwork that you have at your local precasters and work with them to see how you can modify that formwork easily to be able to optimize your UHPC sections. And if you're looking for, or if your agency is looking for more widespread implementation, then it can be advantageous to try to take steps toward a standard section shape, like FDOT with their H piles. And there are a lot of short span bridges, so we see short span bridge solutions as an early maybe more widespread implementation opportunity as well. A few examples. The first here is a modified Minnesota 54-inch bulb T section. So with this, more details are in this report highlighted here, but you can take the side forms, slide them in to reduce that web width, add some blockouts in the top to get this optimized section with a 3.5-inch web and 21-inch top flange. So these modifications to the formwork reduce the weight of the section by 27%. If we add a conventional concrete cast in place deck on each section, the conventional concrete beam on the left, UHPC here on the right, and for UHPC section, if we use 7/10-inch diameter strands instead of the 6/10-inch for the conventional concrete, we can increase our span length from 128 feet for conventional concrete section to 160 feet for our UHPC section. So we can see we can increase our span length by about 25% while maintaining that 64-inch depth. Another example is shown here. So if we take a standard box beam section, if we increase the size of that foam blockout in the middle, we can decrease the web widths to 3 inches and the top and bottom flanges to 4 inches to reduce the weight of the section. On the left and right are equivalent designs. So the left, a 33-inch deep box in an adjacent box configuration with a composite 6-inch conventional concrete deck is equivalent in terms of designs with a 33-inch deep UHPC box placed in that adjacent box configuration. So you can see, comparing these two, we're 6 inches shallower and 43% lighter using the UHPC section. We can also compare to adjacent boxes that are connected with transverse post tensioning and no cast in place concrete deck. And you can see we're still, we can get equivalent designs with UHPC that are still 6 inches shallower, and in this case, 27% lighter. We recently released a report to try to assist with the section shape selection and design of short span bridges, as we see this as kind of an early implementation opportunity. So in this report, we have a few different section shapes, which I'll show on another slide, allowing for bridge design up to 125 or 140 feet, depending on your deflection limits. And then we try to highlight a couple of case studies where we think UHPC can be used. Here's a summary of some of the possible section shapes that are included in the report. So we tried to take some of these are examples of forms that a precaster may have. So again, the modified box beam where we increase the central void, or a modified voided slab where we increase the diameter of these voids. We also looked at, could we modify, many precasters have next beam forms. So how could we modify the section while you're still using those forms? So maybe we can add some blockouts on the sides of the webs, or in the middle of the webs, or on one side of the web. And you can see this shape here has a very similar shape to that pie girder. That was one of the early built UHPC structures. Another multi-stem T-beam section here. This is similar to the Michigan triple T section that was built a year or two ago. We developed a couple different design aids for each of these sections in the short span bridge report. One being possible span lengths that we can have and achieve for each of these section shapes. Note that with UHPC, because we have a much shallower, or we can have a shallower beam profile for longer span lengths, we're going to start running into those optional live load deflection criteria. So here you can see you can get about 125 feet with box beams until you run into the live load deflection criteria. These design aids were used, or were developed using a calculated modulus and gross section properties. So again, you would have the opportunity to kind of get a longer span if you measure your modulus and you sharpen your pencil and use transform section properties. But you can see here some of the possible span ranges with some of these sections. In the report, we also highlighted a couple case studies where we think UHPC would offer some advantages over conventional concrete. So one here, if your goal is to reduce your superstructure weight, maybe you want to try to reuse your substructure and you can't with a conventional construction, you may consider using UHPC. Also in the same example, maybe you have a low overhead clearance for the roadway underneath. So if you wanted to increase that, you can get a shallower bridge profile using UHPC. So again, if we're looking at a 120-foot span, the left and right would be comparable designs. With conventional concrete, you would need about you'd need a 42-inch box with a 6-inch cast-in-place concrete deck. With UHPC in an adjacent beam configuration, you need a 42-inch depth superstructure or beam depth. So as a comparison, we can compare the overall superstructure depth and the weight here. We can see we're 6 inches shallower with UHPC and much more significant. We have a superstructure that's 41% lighter using our UHPC compared to conventional concrete. There are a few other case studies that we'll highlight in that short span bridge report highlighted here. The first, Rafik mentioned it, about potentially increasing your span length so that you can eliminate a pier in the water. Maybe you have some scour concerns, or you just want to eliminate any substructure elements that are in your water. You could potentially span it with UHPC without increasing the level of the approaches. Also, potentially going from a 4-span to a 2-span bridge configuration, eliminating some of those shoulder piers and adding some lanes underneath could be another opportunity for using UHPC. We also highlight weight savings of different short span slab beam alternatives that you can have with UHPC compared to conventional concrete design alternatives. And then also a case study highlighting how you can increase your hydraulic clearance as well. Another decision that needs to be considered during the preliminary design steps is what properties you're going to use in design. So there are minimum values or values that you calculate using the AASHTO UHPC guide spec. And then there are also typical ranges of available UHPCs that are in the market. So as a designer, you can choose to use the minimum properties, and these values are, again, the minimum values would be specified in the UHPC spec, or a designer could survey the available UHPCs that may be used in a project, maybe talking to local precasters, getting their qualified mix properties, and then use the kind of the minimum ranges of those in design. And there can be advantages to assuming different design values, or there can be advantages to assuming or using the minimum of the available design values instead of the minimum values overall. So as an example, as I talked about, deflections can be one of our limiting criteria. If you measure and you know your local materials are a little stiffer, then that can allow you to have longer spans while still meeting the live load deflection criteria. Material conformance is another important topic related to the selection of UHPC materials. And when we're talking about material conformance, it's a little bit different than conventional concrete. So with UHPCs, there are two stages in the material conformance process. There's a material qualification process where UHPC materials need to undergo a set number of tests, or a certain type of tests and a certain number of tests to qualify as a UHPC material. And then there are material acceptance tests. And these material acceptance tests are designed to make sure that the UHPC that's used on a project that's used to cast members has the material properties that you assumed in the design process. So FHWA worked with AASHTO to develop material conformance guidance. This has gone through the balding process and passed COBS in June, and will be forthcoming in the next release of the UHPC guide spec. All of this material conformance guidance was based on an extensive experimental testing program, and kind of all based on trying to create a statistical level of confidence in the qualification and acceptance stages. The next step in the design process is to calculate the demands on the structure. In terms of our loads and load combinations, these are going to be the same as conventional concrete. So we'll use the same procedures that we do in conventional concrete design for UHPC members. Similarly, the distribution factors, we can use the same distribution factors that we use for conventional concrete when designing UHPC elements. The differences between the two design procedures are highlighted here. So with UHPC, it's a denser material, so we need to use a higher density in our design. Additionally, with UHPC, we're going to use a refined analysis procedure for calculating our losses. And because of that, we're going to use our live load factor equal to 1 instead of having the option of 0.8 or 1.0. So in the workshop manual that I'm highlighting here, we have many tables like what I'm showing on the slide to help to compare and contrast the design of conventional concrete members with the design of UHPC structural components. The next step in the design process is to estimate your reinforcement. And often as designers, we may go to design aids to help us with the estimation of reinforcement. We tried to develop some of these design aids for some of those standardized section shapes that we were showing on the previous slides. So as an example here for UHPC, you can come in for different span lengths and see the area of steel required. Again, the UHPC section is 6 inches shallower and 43% lighter than the conventional concrete section. And because it's shallower, deflections become a controlling criteria after a certain point. The complete design table for this example is highlighted in the workshop manual. We also developed similar design aids and design tables for other section shapes, other depths, other span lengths in this section shapes for short span UHPC bridge report that you can search for using the report number. The next step in the design process is to check your service limit state stresses. And essentially, you're going to have the same procedure. You'll still need to choose gross or transform section properties. You still need to calculate your pre-stress losses. You'll still calculate your stresses using elastic beam theory. The difference is you compare these against different stress limits. So your compression stress limits are going to be the same as conventional concrete. Your tension stress limits are a little bit different. Because you're measuring the tensible strength during the material qualification process, you can use that cracking strength as your tension limit instead of a value that's based on the compression strength of your material. The other slight difference is with UHPC, we're going to have narrower webs, less shear reinforcement. So we need to make sure that our beams don't crack under service loads. So because of that, we need to check the principal stresses in our webs. And we'll do that using the principal stress checks that are typically only used for post-tension members. So as I said before, one of the differences with UHPC at the service limit state is that we need to check these web shear stresses. And the reason that we need to do that is because our UHPC members are likely going to have little or no shear reinforcement. So this is one of the main, or one of the big benefits of using UHPC. So we can either reduce or even completely eliminate the shear reinforcement in our beams. Also, our UHPC elements are likely to have thin webs. And because of that, we don't want them to crack at the service level or service limit states. So this check helps to ensure that. Next, we would check our fatigue limit state stress checks. Just like conventional concrete, we need to check fatigue 1 for UHPC and compression and the embedded reinforcement and tension. We also need to check the UHPC in tension and make sure that it doesn't crack. So we're counting on our UHPC, we're counting on the tensile strength of the UHPC in our strength limit states, and we want to make sure that it keeps those tensile properties after millions of cycles. So this limit helps to ensure that conservatively. Next, we have our strength limit state checks. We'll have both our flexural strength and shear and torsional strength limit state checks, just like with conventional concrete. In terms of flexure, one of the differences with UHPC is with conventional concrete, we have the option to use what's called the strain compatibility approach. With UHPC, we need to use the strain compatibility approach. This approach, we start with an assumed strain profile. We use our stress-strain relationships for our different materials to go from strain to stress in our UHPC, steel, and pre-stressing. We take our stresses times our areas to get our force components, and then use equilibrium to kind of adjust our neutral axis steps, and then ultimately calculate our moment and curvature that are associated with this. Using strain compatibility allows us to advantage of the tensile properties of the UHPC, and it also allows us to capture different failure mechanisms that may occur in the member. So with UHPC flexural members, they're generally going to fail because we exceed the tensile capacity of the UHPC. So we can capture that using strain compatibility. But we can also capture if concrete crushing controls or if the rupture of our reinforcement controls. So strain compatibility is a really versatile analysis approach. In terms of shear, we're going to, again, use a strain-based design approach, and we'll use a kind of a modified compression field theory-based approach, just like conventional concrete. One of the main differences is the resistance mechanism. So with conventional concrete, you have your shear crack, you have sliding along that shear crack, and that interface shear is what's going to resist your shear. With UHPC, the fibers keep your crack tight, and UHPC itself has a high tensile strength. So that's going to be our primary resistance mechanism. Rafik and Ben, they went through the derivations starting with MCFT and leading to some simplified design equations that we can use to calculate our shear resistance that are shown here. So there are equations and simplified tables that you can use as well for calculating your shear resistance. The next step in the process would be to do your deflection checks. We need to calculate camber and our long-term deflections. We can do that the same as conventional concrete. And then we can also calculate our live load deflections, which would be the same as conventional concrete. As I've mentioned a couple times, UHPC members will or can have shallower profiles, so deflection limits can control. And so this makes the modulus of elasticity more important. So we can see that deflections are inversely proportional to our EC. So if we increase our EC by 10%, then we'll decrease our deflections by about 9%. So what this means is that if having a stiffness, or if we have a baseline stiffness of, with a K1 of 1, we may have a max span of 95 feet. If we increase that stiffness by 10%, we can get a max span of 100 feet. If we go up 20%, we can get another 10 feet out of it, so 105 feet. So again, something else to consider. You may want to measure the UHPC or use the modulus that's measured in the qualification process. Or, again, you can use, these were all developed using gross section properties. So using transformed section properties or allowing the use of transformed section properties can also allow for longer spans. To wrap up the presentation, we can remember that there are many similarities in the design process between conventional concrete and UHPC members. So if you can design a conventional concrete beam, you can design a UHPC beam. And there are many similarities between the guide spec for UHPC and the LRFD bridge design spec. So if you can use bridge design spec, you can use the guide spec as well. And we can also remember many of the advantages that are used, or many of the advantages of UHPC primary structural components. So they have higher strengths, which allow us to have longer spans, maybe to eliminate intermediate supports. We can have shallower sections to increase overhead clearance and lighter superstructures overall to reduce the demand on the substructure. We can also have improved durability, which can result in much longer service life for elements that are commonly susceptible to corrosion, and also structures with high importance. So with that, I'll conclude our presentation, and I have our email addresses on here. If you have any follow-up questions and want to reach out to us, feel free.
All right, Dave and Rafiq, thanks a lot. Excellent presentation. You covered lots of material in a very short time, but gave the overview of the entire process. So at this point, we are gonna turn it to Paul Lyles to moderate the question and answer period. Now, I stand one correction. If you have any question, like Dave mentioned, his emails and Rafiq's emails is on the screen. Please send the email to Dave or Rafiq in case we don't get a chance to answer all the questions that has been submitted. So by that, so Paul, it's all yours.
Okay, David and Rafiq, very interesting. We'll get into the questions. We got some beforehand, before the webinar started. We've also got a bunch so far, and we'll probably get a bunch that comes in during the Q&A. So here we go. First question just came in earlier before the webinar started. It says, can you compare the fire resistance and rating of UHPC to high performance concrete? And are there any special considerations for UHPC structural components in fire scenarios?
Yeah, I can take that one. So so usually when you're expecting fires and you wanna design, like, consider that what you add is polypropylene or plastic fibers. So basically, UHPC, have the extremely dense matrix. So the water in it, you need to provide, and it's nearly impermeable. So when during a fire, the water vapor needs to go somewhere. So to prevent the the undesirable spalling that you want in UHPC, you add in those fibers. Those fibers during a fire melt and provide like those micro gaps that where it's a place where the fibers or the steam can go, so that you can reduce or eliminate or reduce or prevent the excessive spalling that you don't want in a fire. So that's what they usually do. They add these plastic fibers for fire resistance.
Oh, okay. There's another question that came in, and it asked about acid spills. Does that affect the UHPC?
So UHPC is still a cementitious material. So anything that affects concrete, and it still affects UHPC in terms of chemical attacks and stuff like that, where the durability of it's any water or chloride. Those are where UHPC shine and can prevent water ingress and stuff like that. But any chemical reaction that would happen with concrete would still happen with UHPC.
Okay. These are still beforehand questions. It said, would it be feasible from a cost standpoint to start incorporating UHPC in bridge design?
So I guess UHPC is more expensive than conventional concrete. But we tried to highlight there can be other cost savings in the overall project, or if you look at the overall service life of the structure. So if you have cost savings in other aspects of the project, we think that it can lead to kind of zeroing out. And if you consider the service life, then maybe you can have even some cost savings.
Okay. Then what are some of the advances made in UHPC over the last 10 years?
I think Ben highlighted a lot of these in his intro, and we tried to touch on some of these during the presentation, but there have been a lot of advances in terms of research, from a material standpoint, going from just a few proprietary mixes to non-proprietary mixes, to kind of refining some of those things. From a structural standpoint, going from some of these early applications, specific research and applications for connections to link slabs, now structural components. So I mean, a lot of advancements, a lot of them are summarized in the research reports that from Turner Fairbank, and some of the materials that we also highlighted in this presentation. And there's still some research efforts that are going on now to continue to fill in some gaps and help with deployment. So more to come as well.
Okay. Is it possible to use UHPC for longitudinal joints or longitudinal closure pores on bridges?
Yes, that's a great application. And many or most of the early applications of UHPC have been for longitudinal closure pores or joints in general between prefabricated elements.
Okay. How do the UHPC pre-stressed girder fabrication design requirements compare to traditional pre-stressed girder fabrication design requirements? They were interested maybe in compressive strength at pre-stress release.
Yeah, so I mean, a few different, in general, it's the same, but there are a couple of differences. So obviously the composition of UHPC, as we mentioned, is a little different. So you'll need to figure out how to mix the powder, and then you add the fibers, and then adding the fibers. So that's mainly the new thing there in terms of mixing, and you can still mix it in a centralized mixer and a precast plant, or in a truck, just in a concrete truck. In terms of the casting process, it's self-consolidating, so you should not be internally vibrating, because that would disturb the fibers and they would sink. So you don't need to do that. So if you feel like you need to provide a little bit of vibration, you can tap the sides of the mold just gently, but that is it. In terms of pre-stress release, typically the creep and shrinkage models that are right now in the guide spec, they work for 14 KSI minimum at release. You don't have models right now, at least provided by AASHTO, that tells you how to design for creep and shrinkage before. So that's why, in a sense, you will need to specify the compressive strengths at pre-stress release. And usually it's taken as 14 KSI. If you do that, you can use that the tensile capacity at release would be 0.75 of the tensile capacity of the material. So you don't need to test for that. You just make sure compressive strength 14 KSI, and then you can take the tensile strengths to be 0.75, whatever you design for at mature level.
Okay. When using UHPC for a closure pore between precast deck panels, what would the cure time be compared to maybe like high early strength concrete?
It really depends on the UHPC mix. I mean, you could see a mixture that with no special curing, so just ambient cure, you can get it to have, by using different super plasticizers, just like in conventional concrete, you can get an early strength that you would need probably 12 to 14 KSI to open the bridge to traffic in these situations. So you could probably get it in 14 hours to 16, 18 hours, but you will have to kind of specifically request for that, because there's not, the UHPC mixture is not unique. Just like in conventional concrete, you will have to get a mixture that is designed to have such an early strength within those short time that you need probably for a closure pore.
Okay. What applications are there for UHPC and bridge rehab and repair? You mentioned some of those. Do you want to comment on that?
Yeah. So here are some that are highlighted. Overlays, link slabs, beam end repairs, connection repairs are some of the primary ones right now. I'll mention that this was part of an Everyday Counts 6 initiative. So there's a nice report summarizing a lot of this work from Haber and other authors at Turner Fairbank. So you can look for that online and see a lot more information on these rehab and applications.
Okay. We had a question here, and it says, please discuss the use of plastic fibers rather than steel fibers. You talked about using the plastic fibers in fire, but what about just using them in lieu of the steel fibers?
Yeah, so in the guide spec, it says that the steel fiber reinforcement must be included, and then they must be the primary resistance mechanism to resist tension. So it doesn't disallow you to not having plastic or polypropylene fibers or anything like that for fire resistance or whatever, but you can't depend on them tensile capacity. That's right now there's not a lot of research, so I actually felt like they will just say steel fibers for now, not go into the the tensile creep or all that that are still unknown for plastic fibers, or not enough research out there. So that's how they reached out the conclusion that steel fibers.
Okay. The UHPC code says freshly placed UHPC may have reduced tensile strength from fiber orientation. How do you control this property in the field? And does this cause problems in link slabs?
The main way that you control this is your casting procedure and casting method. So generally, you want to place your UHPC at one point and allow it to flow along the length, or you want your UHPC to be cast into already placed UHPC. So this will allow your fibers to be aligned in the right direction and give you the tensile properties that you need. And there are some states that have done lots of link slabs where you're casting UHPC on one side of the link slab and allowing it to run down the length, and they've seen good performance in those link slabs. So I'd say, what you want to avoid is, if you're casting a structural component, you don't want to cast from both sides and have the heads of the UHPC meet in the middle. So that should be avoided. But in general, casting procedure is how you would control that.
Okay. And then you said earlier about avoiding vibration.
Yes.
Can this product be bonded to regular reinforced concrete piers with exposed reinforcing for a sustainable repair?
Yeah, in slide 8, I think I show a picture of it. We show a picture of it, but yes, just like overlays, what you need to do, you need to remove the bad concrete from your pier, then expose the coarse aggregate in the UHPC, and expose the coarse aggregate in the existing concrete, so you have good concrete, exposed aggregate concrete, and saturated surface dry, and then you can place the UHPC, and usually you get a good bond for that connection.
Okay. Regarding fiber content by weight, the old connection information had a 2% lower bound. Is this still required?
I think that maybe this referred to the ABC guide spec that was published in 2018. So in the 2018 guide spec, the material section, it doesn't have any tension property requirements or criteria. So I guess the guide spec was developed on certain mixes and had a 2% fiber criteria. The updated UHPC guide spec it doesn't have any minimum fiber content criteria, but it does have the tension property criteria. So if you're doing connection designs, I think it's still okay to use the criteria that are in the guide spec. If you wanted to also test your tension properties and use the UHPC guide spec, then you could do that as well.
Okay. Question came in. We're into questions now that came in during the presentation, but it says, how flexible are steel fibers? 30 years ago, Florida DOT used UHPC, and we heard from contractors that finishing concrete was difficult due to steel fibers. What has changed in that regard?
They're steel fibers, so they still have they're high strength steel. They're short. I'm not quite familiar with originally the mix design came a long way right now, so I guess the mix composition is a little bit better. The UHPC started about 30 years ago. It was called reactive powder concrete before, and then along the times there was some refinement in the mix composition. Right now, you still get at the surface at the end. You still get sometimes a what they call it, like elephant skin, or a bad surface, because it's self-consolidating as the air bubbles goes all the way to the top. So you can tap the surface or screed it just like you do, but that's how they usually do it these days. But in terms of mixing, those have all been figured out. Short fibers, steel short fibers inside, and they've been figured out how to mix it and make it all, a consistent, uniform material.
Okay. When there is corrosion, how does the UHPC with steel fibers perform? You had a picture of that in the main thing, and it looked like it held together. You could just see a little rusty spots on the top of it, but it was pretty good.
Yeah, so the corrosion, if there is a fiber at the surface, it will corrode and it will go away, and you will have that is what you see here on the screen. There's a stain. It's a brown stain of the fibers. The fiber's not there anymore, but that is the extent of the discoloration or the protrusion into the specimen. So just surface, because mainly cosmetic thing. Nothing that the water won't go inside.
Okay. Question came in and says, what is the cost difference between a UHPC deck overlay and latex modified concrete overlay?
Yeah, I'm not sure.
Okay. It may be more expensive, but it may last longer. So whatever.
Yes, it would last a lot longer.
Yeah.
There's a nice cost comparison that was done for the Delaware Memorial Bridge. So I think you could search for that. That was again a report by Dr. Haber, and the Delaware Memorial Bridge ended up using a UHPC overlay compared to a couple different alternatives because they determined it was the least expensive of the options.
Okay. Another one came in. Have stability analyses been during transportation and handling been performed for the optimized PSC beam section you showed with increased span lengths?
I didn't quite. Maybe David. I didn't quite hear the answer to the question. Go ahead.
They haven't been, but the methodology that PCI has put out recently could still be applied for the UHPC sections as well.
Okay.
Just modifying the section properties for your optimized UHPC section.
All right. Also, UHPC helps to increase span lengths for a given structure depth. How do they affect the deflection, live load vibration, or fatigue related concerns? And do they still satisfy the AASHTO minimum structure to depth ratio?
My understanding of AASHTO is that there's an optional live load deflection criteria in the article here, so L or 800. And, states are free to enforce that or not. I believe that most states do. And you can see that, your deflections will, because you have a shallow recession, your deflections do control after a certain point. So again, you can use the actual UHPC material properties, which are typically stiffer than calculated, and that'll allow your deflection or allow for longer spans while meeting deflection criteria. Or you can use transform section properties, and that can allow you to get those live load deflection limits to check.
Okay. Has the FHWA or any other official publication released a report on the ultra girder design concept for a 300-foot span, single span referenced on slide 15?
Yeah, for the 300-foot girder, we published a journal paper back in, I think Ben and I published it back in maybe 8 years ago, something like that, right before the guide. What you will see is, I think, a design, the FHWA, in one of the reports, you'll see one with a conventional concrete deck, like an I-shaped girder, based on the Minnesota MN54 or MN64, one of those, and then it spanned 160 feet. The 300-foot, you'll see just a summary as a conference paper. The ones you're seeing here in the picture, so the one on the left, that one, and the first two. So the smallest one there is 32 and then 32 inch high, deep, and then that one is 43 inch deep. Those were tested at Turner Fairbank. And then those are published. They're tested in flexure and shear. The deeper one, the 73 inch, we still have them in the lab. We're planning on testing them within 6 months to a year.
Okay. Have any of these seen any actual deployment?
Those specific shapes, no. The deployments, there's been other I shapes that were done in Iowa, yes, and those varied between 40 inches to, I think, 30 to 40 inch deep. So yeah, the first deployment was an I girder, the second was an I girder, and then you'll see the pi girders. The last one was a triple T, the one in Michigan.
Okay. The question came in about how does UHPC perform when exposed to de-icing salts on highways? You showed the pictures of the ones that's up in Maine that were immersed in salt water, but how does that compare to de-icing salts on the highway?
It's a liquid, so it won't go inside that's why it's been used as an overlay, for example, on the Delaware Memorial Bridge. It just won't go inside into the chloride won't go inside more than usually what the tests have shown, like 5 millimeters max, and then it stops. So it's pretty small, so that you should be protected. That's one of the main reasons why UHPC has been used in overlays.
Okay. Then this is going to regard box beams. Is an overlay required with UHPC box beams? And how do you achieve acceptable cross slopes and the riding surface?
I'd say an overlay is not required. I mean, and in terms of construction challenges with adjacent beam configurations, you'd have the same challenges with conventional concrete. I guess a lot of the times when you're using the UHPC as your riding surface, you're going to grind off the top quarter inch or so. So this would be kind of planned into the casting of the beams, the casting of the joints, and then that would help you to achieve the desired profile within your required or your necessary tolerances.
Okay. Sometimes they groove the decks, or in grinding it, does that about the steel fibers affect that at all?
We've heard, so I mean, largest deployment for an overlay application where they had to grind and groove the surface was the Delaware Memorial Bridge project. So we've published some different things on that project, but we've heard they've been able to use the same equipment. They had to use a certain grinder head. Some of them would wear out quicker than others, but there are ones that are easily available. Just like some aggregates harder than other aggregates. So there are ones that are available. And I guess, yeah, there's some guidance that we provide on like priming the line before you start pumping, the fibers through it so that you don't get any clumping in it.
Okay. Do you know of any use of UHPC for railroad bridges using ARIMA code and loading?
I know that ARIMA is looking into UHPC. They've came to our lab a couple of times. They're looking into incorporating UHPC into their their codes. In terms of structural, you'll take the loads from, in terms of structural design, this guide still applies. The concept's still the same. You need to find out different loads. But I know they're looking at it.
Okay. It's 19 after. I'm going to go ahead and let Rick Leptic come in and see how many more questions we've got. Rick, you want to come on?
Yeah, there's a lot of questions, Paul, but we'll sort through a few of them here as we wrap it up. One question to build off that ARIMA question, I did see a question relative to other building codes, say not just bridges, but other structures, say parking decks, buildings, whatever. Do you know of any discussion going on widening the use of UHPC into other sectors?
I know PCI have a committee on UHPC trying to look at some of that. Also, I mean, ACI, I also involved in ACI working on a guide spec for, in guide. It's non-mandatory, so it's a guide in the committee, ICI Committee 239, that's working on Subcommittee 239C on structural design with the UHPC, working on a guide. But with ACI, it takes a long time. But
sure.
Yeah, I mean, generally, I can say the concepts that you'll see in the AASHTO spec would still apply for any structural component, whether you're using it for vertical construction or bridge application.
Okay. And with that, I guess is, I don't know if you mentioned it, but say some of the overlays and things like that, can this UHPC be pumped like with normal equipment, like concrete is pumped to get to on a job site?
Sure. I mean, yes. You need to alter the mix design a little bit, but UHPC suppliers can provide pumpable UHPCs.
Okay.
It's sprayable too, so that's pumpable.
Sprayable.
And sprayable as well. Yeah, as you saw earlier.
Yeah. The say the creep and shrinkage behavior of the UHPC, is it similar? And in those properties, it kind of probably goes into the pre-stress losses, on the girders and all those kinds of things when all those other different properties.
They're different, I'd say, but it's not mix specific. You'll see, I mean, the design, the guide spec has models that tells you in general how they behave, but in general, I mean, some UHPCs they will shrink a little more than some concretes, and some of them will shrink less than concrete generally. And in terms of creep, it usually, I mean, as a factor, it creeps a little less, but you can put more stress and force in it, so that the value of the stress that you can put on the UHPC is higher, so you may see a little bit more creep, but that doesn't jeopardize your structural design. You still can take benefits of those added strands that you can put there and that cause the extended span and all that.
So looking at the design service life of a standard concrete beam, say, versus one with UHPC, what's the, what is there I'm assuming there's quite a difference, but just curious how that's looked at. Says the design service life, I think he means performance, actually the service life, just plain service life of the girder with the UHPC versus what we're, standard concrete.
Yeah, I think what David is saying is look at the diffusion coefficient, and you'll see that it can live a lot longer. But I mean, a lot of people have done that, and I mean, they're saying 1,000 years. But I would say if you say you want to design it, it lives. If you're designing a bridge for 100 to 150, I think comfortably you can say that a UHPC bridge will live like that. That is
Longer.
A reasonable number. Yeah.
Just given the permeability and everything else and the strength of it, you should get a lot longer life out of it. So when it comes to software designing these girders, is what UHPC girder design, I mean, can you just use some of the standard software, or is there do you have to get a specialized program in order to design those girders?
I would say that the PG Super is a software by WashDot. It's available for download that has the UHPC module. You generally need to look for softwares. I mean, the guide was published in 2024, so I don't know how many software have picked up a UHPC module in it, but there are some differences in the flexure and shear design so you would need to look for ones that have that design in them. PG Super is one of them. As David mentioned, the way you get the loads and stuff, those existing software can still work because there's nothing there.
Yeah. Okay. I know you mentioned that the steel fibers are high strength, but what is potentially the yield strength of those fibers?
I think that they report them in terms of ultimate strengths, about 200 to 300 KSI. I may be wrong, but that in that order or more. Yeah, about 300 KSI. I think about 300 KSI. Yeah.
Okay. Oh, here's a good one. So as we move, into using UHPC more, there was a question: should states develop their own non-proprietary mixed designs for in their contracts versus using proprietary designs or proprietary mixes, I should say?
I mean, they can do either. That's the beauty of performance spec. That the guide is if you can. I mean, they're all at the same footing. They have to go through the same testing requirements and report the same properties. And then obviously the commercial one and the non-proprietary will have a cost associated with it. So it's up to them. I can't comment, but they'll have more information that they can make decisions available to them because of this performance spec requirement. So any UHPC mixture that follows this process it passes the minimum requirements in the guide, they can use the guide.
Okay. Field testing. Obviously, when we're placing concrete in the field, we have current testing that we do. Is the testing for this UHPC being used in the field, is it similar, or is there special tests that we'd have to do?
There's one test that is addition. I mean, you still do the tension. I mean, so there's the flow test. There's the material conformance guidance that is just passed with AASHTO has all the information. I mean, there's the two tests. One that does the flow. It's a table, and then we're going to go into the HPC. So the flow test. There's the penetration resistance test that tests the fiber dispersion or fiber segregation potential. So those are the two fresh properties. And then in terms of hardened properties, you will have the compression strengths and one option. There's 3 options in the new material conformance for quality control. You can do the retention test, which is probably more expensive. You don't want to do that every time during production. What you can do is a simple flexure test. There's 2 options for flexure.
So as we're getting close to wrapping it up here, there's still a lot of questions, but some of them, similar slant. But there's one here that I thought would be a good one to kind of finish up here. What do you think the next major or technical leap in UHPC might be? That might be on the horizon, or is there anything that could make it better, I guess, or whatever?
I think the technology got to a point where, we have a design spec, we have a material conformance spec, people have used it. I think it's time for us to think how we could utilize it and where it's best to be utilized. If you have a bridge over salt water, if you're driving piles in a salt in a marine environment, if you need a little longer span, if you can take a bridge out, that I think thinking where UHPC can work to solve an existing problem or can help make something that we're starting better that we're building today.
That's great. Adirad, I guess we'll turn it back to you.
All right, thanks. This was an excellent presentation. The questions are still coming, and as Rafiq and Dave mentioned, they have their email address on the screen. Please, by all means, send your question to them, because we are not going to, for this particular presentation, we are not going to be providing the answer to the questions that we did not get a chance to provide the answer on our website, but you can send the email to Dave and Rafiq, and they have agreed to correspond with you. So on that note, we will conclude this webinar. Again, Dave and Rafiq, excellent. Well, lots of material. You guys covered lots of material. I was amazed how much material you were able to cover in such a short times. So on that note, we are going to conclude our webinar today and hope to have you with us next month. Thank you.